You are welcome once again to the University of Mathematics. And in this tutorial, we are going to look at types of relations. From the beginning of this lecture, we looked at relation R, and we defined relation that it is the cross product of a set A and B such that it produces an ordered pair A, B, given the element A is from the set A and B is from the set B. Today we are going to take this a little further, and that brings us to the types of relations. And in the types of relations, we are going to look at reflexive, we will look at irreflexive or anti-reflexive. We will also discuss symmetric, anti-symmetric, and asymmetric. And lastly, we look at transitivity. These are the types of relations we are going to look at in this tutorial. Let's get started. Starting with reflexive. Let's say a bijective mapping of A to itself is given as A cross A. So typically we are looking at a relation taking a set A and mapping it to another set A. And this is going to give us A, B, such that A is coming from the set A and B is also coming from the same set A. Okay, so when we talk about reflexivity, all we are trying to say is that given the set A, the relation R defined on the set A is said to be reflexive if and only if you pick any x in A, x, x is a member of the relation R. If and only if you pick every member belonging to the set A, that particular member maps to itself. For example, given a set A equal to 1, 2, 3, and 4, if you want to define a reflexive relation on A, then that relation, say R, must contain these elements. Since we have 1 must map to itself. Since we have 2 must map to itself. Since we have 3 must map to itself, and 4 as well must map to itself. In a nutshell, every element X must relate to itself for all elements in the set A. So, a reflexive relation on this set A must contain the elements 1, 1, 2, 2, 3, 3, 4, 4, as well as other elements or other possible pairs. But all of these members need to be in the relation. If you have 3 appearing and remaining 1, it is still not reflexive. Every member in the set must relate to itself. Let's take an example. For instance, if we have a set A to be equal to 1, 3, 5, 7, and we have relations R1 given as, is this relation reflexive on the set A? We just said that a relation is said to be reflexive if and only if for every element X in the set A, it means that X is related to X. in a nutshell, we have the ordered pair x, x for all x in A. So, looking at the sets we have been given, we have elements 1, 3, 5, and 7. And so, for any relation on the set A to be reflexive, it means that it must contain the elements 1, 1, 3, 3, 5, 5, and 7, 7. If it contains up to this and this guy does not appear, it is still not reflexive. It must contain every element mapping to itself. Otherwise, it is not reflexive. So, we have 1, 3, 5, and 7. In the relation, we see 1 map to 1. So, that is checked. We move to 3. It means we are expecting 3 is to 3. 3 is to 3 is not in this relation. So, it tells us that since 3 related to 3 is not in the relation R1, then we can conclude that R1 is not reflexive. You don't even need to bother yourself looking for the other members. Since one of them is not, you can boldly conclude that the relation R1 is not reflexive in this case. Considering the same set, let's take another example. Let's take R2 to be defined as, the case is still the same. We are still defining R2 on the set A. We are expecting to see 1 related to 1, 3 related to 3, 5 related to 5, and 7 related to 7. All of them in R2 before R2 can be reflexive. But what do we see? Let's take 1. Do we have 1 relating to 1 in R2? The answer is no. So quickly, we can conclude that R2 is not reflexive. There is no need looking for all the other members. But again, for the sake of learning, we can check. Let's go to 3. In R2, we don't also have 3 relating to 3. That also confirms the fact that R2 is not reflexive. And in fact, 5 is to 5 is not also in R2. And as well as 7 related to 7 is not also in R2. So we don't even bother ourselves moving around doing the same thing. We can conclude straightforward that R2 is not reflexive. Let's take another example. Given R3 on the same set A as we have this. And bear in mind that our set A is given to be 1, 3, 5, 7. So like I said, we are expecting that for R3 to be reflexive, we need to get each element of the set A mapping to itself. To it, we are expecting to see 1 relating to 1 and 3 relating to 3 and 5 relating to 5 and finally 7 relating to 7, all in the set, all in the relation R3. These are the only things we are looking for. And if we are able to find them, then we conclude that R3 is reflexive. So 1 is to 1. Here we go. 3 is to 3. We have it here. And 5 is to 5. We also have that one here. And 7 is to 7. That is also here. So since all these belongs to R3, we conclude that R3 is reflexive. This is the case that you'll be getting numbers. They can take you into the field of vectors, or they can take you to the field of polynomials. They can take you into the field of lines. I mean, everywhere at all. Whichever case you find yourself, every element compared to itself should obey the rule. Let's now look at irreflexive relations. A relation R defined on the set A is said to be irreflexive if and only if for all elements X belonging to A, X, X is not a member of the relation. In other words, X is not related to itself. Unlike reflexivity that every member needs to relate to itself, irreflexive relations, no element should relate to itself, not even one of them. So let's take, for instance, our relation R1 to be equal to 1, 2, 1, 3, 1, 4, 3, 2. Let's work with this example. We are saying that no element should map to itself, or no element should relate to itself. So in this case, we have seen that we are having 1, 3 in the domain, and in the range, we are having 2, 3, 4. Okay? Since we have seen 1, it means that we shouldn't see 1 related to 1. And we shouldn't also see 2 related to 2. And as well, we shouldn't see 3 relating to 3. And we shouldn't see 4 relating to 4. None of this, not even 1, should appear in the relation. If they appear in the relation, then it has nothing to do with irreflexivity. None of them should appear. So, if we look at this example, in the relation R1, we don't have this, we don't have this, we don't have this, and we don't have this. We can say that this is irreflexive. Note that if even one of them comes in the relation, then it means that it is not irreflexive. Having said this, I want to remind you that we are still under logic and set theory. So the knots of a statement I believe you should know. For instance, I am rich. The negation of this statement is not I am poor. Rather, it is I am not rich. So bear in mind, the fact that it is not irreflexive doesn't mean that automatically it should be reflexive. No. Conditions must be met before we can say that this relation is reflexive or irreflexive. You can't just assume that because it is not the other, then it is the other. Let's take another example. Consider a relation R2 to be, is this relation irreflexive? Go ahead and provide your answer. Okay. For irreflexivity, we are saying that for all elements X in the set A, X, X should not be in the relation R. If you look at R2, we have 1 related to 1. We have 2 related to 3. And we have 2 relating to 4. So we shouldn't see any of these elements relating to itself. However, it turns out that 1 related to 1 is in R2, which confirms the fact that R2 is not irreflexive, and it doesn't automatically guarantee that R2 is reflexive, you need to check the conditions before you conclude. Now, in the next example, we are going to check whether R3 is reflexive or irreflexive. So we check for each case. Is R3 reflexive? And as well is R3 irreflexive? I challenge you to try your hands on it. We state the property for reflexivity. We say that a relation R is reflexive if for all elements of X in the set A, it means that we have X, X in the relation. So in R3, we are expecting to see that 1 relates to itself, 3 relates to itself, and 5 relates to itself. We will look for these 3 guys, and all of them must be present in R3 in order for R3 to be reflexive. Now we see 1 relating to 1, so that is checked. What about 3 relating to 3? That is not in R3. So we say that since 3, 3 is not in R3, and let's look out for 5 relating to 5. Well, that is here. But I told you earlier that if one of the conditions fail, it means that it is not reflexive. So since 3, 3 is not an element in R3, we say that R3 is not reflexive. Let's check for irreflexive. The law for irreflexive states that for all elements X in a set A, X, X must not belong to the relation in order for the relation to be irreflexive. So in the relation, we already see that 1 is relating to 1, which means that defies this rule. So this is an element of R3, and this condition defies the law. So we say that R3 is not irreflexive. It doesn't guarantee the fact that since it is not irreflexive, it is reflexive. Over here, you have seen clearly that R3 is neither reflexive nor irreflexive. So you take note of this.